Okay. Okay. So let's look at here how the electron delocalization, another word would be resonance, affect the frequency of the absorption. Okay, where are we going to see the peaks for these stretching vibrations? Now here the first one, we have 2-pentanone, 2-pentanone. It's a isolated double bond, carbon oxygen carbonyl group, 2-pentanone. And then we have 2-cyclohexanone. Now the second one, you can see, you can draw a resonance structure. Pi bond will break and form a bond, another pi bond between these two carbons. So the carbon oxygen bond will, pi bond will break and gives its oxygen to, gives its electrons to the oxygen. So because we can draw resonance structures for this one, in one instance you can consider carbon oxygen is a double bond, and then in the resonance form it is a single bond character. And we know that it's not that in one instance it's a single bond, one instance it's a double bond. When we learn about resonance, we studied about that, but it is the sum of both of these resonance structures. And the carbon oxygen bond is neither double bond nor single, it's going to be in between, meaning it's going to be weaker compared to a full strength double bond. Okay, now which one is more stronger? Carbon oxygen double bond. Here, since it has resonance, now it's in between double and single. So which one do you think would need more energy to vibrate? The double bond or the bond between single and double? It's the double bond. Need more energy to vibrate, the carbon oxygen double bond. So in a ketone, carbonyl group would appear at a higher wave number, higher frequency, 1720. The stronger the bond would need more energy, appear more frequency, appear at a higher wave number. And then this one, since it's going to be weaker compared to the isolated carbon oxygen double bond, so it would appear at a lower wave number, 1680. Okay, the more double bond character, the greater the frequency. And here we have this 2-pentanone. So the carbon oxygen, the carbonyl group would appear around 1720. So if you have a ketone made from an experiment, that you need to know whether you have made it. Let's say you do a oxidation, alcohol group. You want to do the oxidation, let's say with chromic acid, right? And then it become a carbonyl group, ketone. You want to know if your reaction has gone to completion or the functional group that you want has been made. You run IR, and then you see there is a peak around 1720, and then you're going to be so happy seeing that, yay, I made my carbonyl group. Especially if it was a hydroxyl group you started with, since we don't have a broad OH group here, you're going to be even more happier because excuse me, your starting material has completely consumed. You don't have that broad peak. So that is the beauty of the IR. So you can see quickly if a reaction has gone to completion or you have made the product that you desired based on the functional group. Okay, that's a pure double bond that comes around 1220. And then this one is the cyclohexanone. Okay, cyclohexenone. Okay, and this double bond with some single bond character, remember, due to the resonance, so it appear at a lower frequency compared to 1720, around 1680. The less double bond character, the lower the frequency. Okay, and then resonance electron donation decreases the frequency, inductive electron withdrawal increases the frequency. So we can have some instances. You have a carbonyl group, and then there is you can have an atom next to it, and through resonance it can give some electrons. Electron donate it, and then the carbon and oxygen will become a single bond. So in this case you can have some double bond character and single bond character. So what happened due to that? Resonance electron donation decreases the frequency. If something like this happen, it decreases the frequency of the carbon oxygen double bond frequency. Let's say you have a group next to that is going to inductively withdraw electrons. If it withdraws electrons, then the carbon-oxygen bond will not participate in a resonance like that, and it would remain as a carbon-oxygen double bond. Let me explain this to you in an example. Let's say you have a molecule like this, and then let's say our Z is NH2, amine group, like amide, and then you can have another one like this, oxygen, right? Now nitrogen has a lone pair and oxygen has two lone pairs, and then amide can have a resonance structure. Now between oxygen and nitrogen, which one is more electronegative? It's obviously oxygen. Normally the more electronegative atom would like to have a negative charge on it. It would become unstable if it has a positive charge. You can have a positive charge, but that is not happy. Okay, so let's say nitrogen is going to participate in resonance like this by donating electrons. So it would become like this, O minus, double bond here, and NH2. This would become positively charged, and that is a resonance electron donation by nitrogen. So then you will have these two resonance structures. But what about oxygen? If oxygen going to do the same thing, it would form this resonance structure, O minus, double bond, oxygen. You may have seen, or we are going to see, that the ester, this is an ester functional group on the right, that can have this resonance. But oxygen carrying a positive is not going to be as stable as the nitrogen carrying a positive charge. So it should be a balance between either inductive electron withdrawal dominate or the resonance dominate. But in the case of the oxygen, here it's going to act as a inductive electron withdrawal. This because oxygen is more electronegative compared to nitrogen, whereas nitrogen is going to donate electrons. So if you donate electrons, what's going to happen? You're going to have this resonance stabilization, and then the bond going to be between single and double bond. So the frequency would be lower, right? Yeah, so because it's single and double. Whereas the other one, where we have the ester, it's more likely inductive electron withdrawal. So you can have RCOO. So inductively electron withdraws by the oxygen. So this carbonyl group will more likely stay as a carbonyl group. So as a result, this would have a higher frequency, higher energy. You need to stretch a double bond, higher energy, higher frequency, higher wave number compared to the carbonyl group next to the nitrogen. Okay. So that's what it says here. Resonance electron donation decreases the frequency. Inductive electron withdrawal increases the frequency. Now let's look at carbonyl group next to a oxygen and carbonyl group next to a nitrogen. Okay. Now this is the IR spectrum of an ester. So ester has a carbonyl group, and then you have the oxygen right next to it. That's the electron withdrawing group. So it would be carbonyl group would remain as a carbonyl group. So our frequency or the wave number is going to be 1740 right there. Okay, and this is carbon oxygen. This single bond is you find somewhere here. And then this is an amide group. Amide is, you have the carbonyl group. Now instead of oxygen, you have nitrogen there. So the carbonyl group, so this group is 1660. That's because nitrogen, by donating electrons, makes a resonance stabilized structure where the carbonyl group is now in between single and a double bond. Okay, so it has a lower frequency because now the bond is weaker and it needs less energy, so it has a less frequency and the wave number. Okay, and then we have different types of carbon oxygen bonds. Now this is alcohol carbon oxygen bond, stretches around 1050, and ether again carbon oxygen 1050. And then you have carboxylic acid carbon oxygen, this bond right there. Earlier we were talking about this bond, carbonyl group. Okay, now we are talking about carbon oxygen bond right here. Now remember the carboxylic acid, the lone pair of the oxygen can form a pi bond between the carbon oxygen, making it a double bond. So then this bond will open up. Okay, so double bond. So now the carbon oxygen, this bond has a single and double bond character. So it would stretch at a higher frequency compared to a carbon oxygen bond of an ether or a carbon oxygen bond of an alcohol, 1250. Okay, so that is alcohol, and similar to that in ester also, instead of hydrogen now you have methyl group. Same thing, when we are looking at this carbon oxygen bond, it is resonance stabilized like this, so have single and double bond character, would stretch at a higher frequency. Okay, now don't get me wrong when I said that the ester I have shown here, that oxygen would not keep a positive charge on oxygen. It does happen, but it would be more energetically stable for nitrogen carrying a positive charge compared to oxygen carrying a positive charge. You see it over here like that. And when we are drawing the resonance structure for the ester or the acid, we do put these resonance structures, and we were comparing that with the nitrogen. Okay, so the carbon oxygen bond in an alcohol is a pure single bond, you see, and also the same for the ether, it's a pure bond, single bonds have a lower frequency. The carbon oxygen bond in a carboxylic acid has a partial double bond character. Same with the ester carbon oxygen. One carbon oxygen single bond in an ester is a pure single bond, and one has partial double bond character. So because of that, because of the partial double bond character, it has a higher frequency, double bond character, and then if you measure the frequency of the other one, that would be 1050. Okay. And then hydrogen bonded OH groups are broad and stretch at a lower frequency. Now, you guys remember hydrogen bonds, right? So what are the elements that can form hydrogen bonds? Remember the NOF, N-O-F. When you have hydrogen bound to nitrogen, oxygen, or fluorine, they can form hydrogen bonds. That is a strong intermolecular interaction, kind of a dipole interaction, but we call it as a hydrogen bond when it involves hydrogen with another small electron dense atom like nitrogen, oxygen, or fluorine. Now this is carboxylic acid. Okay, alkyl group, carbonyl group, OH. This is another carboxylic acid, alkyl group, carbon, alcohol group, and oxygen. Now you can see that these two carboxylic acid groups had made a dimer in the form of a hexagon. Normally 6-membered rings formation, even for temporary, is pretty stable. So now you can see the hydrogen bond between the carbonyl oxygen and then the hydrogen of the OH group, and then the carbonyl oxygen of the other acid forms a hydrogen bond with the hydrogen of the other one. Now, due to this hydrogen bonding, what happened to the OH bond? What happened to the strength of the OH bond? Increase or decrease? Now, this oxygen is pulling this hydrogen towards it. This oxygen is pulling this hydrogen towards it. So, as a result, the strength of the oxygen-hydrogen bond decreases. Right? Now, we are comparing this with the alcohol. So, in the alcohol, you have an alkyl group OH, alkyl group OH. The hydrogen bond happened between hydrogen of one alcohol and then the oxygen of the other alcohol. Normally, due to the hydrogen bond, again the bond between this hydrogen and oxygen become weaker. Okay, so but in the carboxylic acid, it happens in two places because it has a hydrogen bonded dimer, whereas alcohol has only one alcohol group. So this bond, the alcohol, not the alcohol, acid OH group would become weaker compared to the alcohol OH bond. So the alcohol OH bond will need more energy to stretch it, and as a result appear at a higher frequency, 3550 to 3200 compared to the acid, that is a little bit less, 3300 to 2500. Okay, more hydrogen bonding. The more the hydrogen bonding, the OH bond will become weaker and it would need less energy to vibrate, appear at a lower wave number compared to the alcohol. Okay, and then let's see the difference between concentrated solution versus dilute solution. Which solution do you think you can have more hydrogen bonds? Concentrated solution, meaning you have more alcohol molecules, or dilute solution that you have less number of alcohol molecules? It would be more hydrogen bonding in a concentrated solution. So then you can have more hydrogen bonds. As a result, OH bond will become weaker, appear at 3200 to 3550. In a dilute solution, it would be a little bit higher frequency, 3650 to 3590. It is easier to stretch a hydrogen bonded OH group. Okay, and that's why we also see a broader peak for the hydrogen bonds, intense but broader. Okay, broad and stretch at a lower frequency. We were comparing these. Okay, and this is the IR spectrum of an alcohol. So you can see the broad OH peak due to the hydrogen bonding. Okay, it's always easy to identify the alcohol peak. It's going to be broader peak appearing around 3400. And then this is IR spectrum of a carboxylic acid. Remember the alcohol we saw around 3400 around the peak area. Now this is little less, around 3000. Broader OH stretch and also at a lower frequency. And this is the acid. 1, 2, 3, 4, 5. This is pentanoic acid. Okay, and this has a carbonyl group, and that is around 1700, a little bit less than 1700, and you can also see the carbon oxygen stretching frequency. Though they were written like this is carbon oxygen stretching, we could identify exactly where the carbonyl is, but the rest of the peaks we might not be able to identify exactly which one is which. And these are some, I guess I can stop here and then start the next session later.